Hi, my name is Timothy Garcia, and my molecule sign was threonine. So, a little background on it: it's an amino acid that we ingest in our body, and we can only get it by eating protein rich foods like fish, meat, chicken, those type of things, because our body won't generate it on its own. And whenever we ingest it and stuff like that, it'll promote collagen and bone flexibility, which in turn will help with wound healing or like repair tissues. And it was discovered in 1926 by a biochemist and a botanist in Imperial College in London. So the way we get the IUPAC name of it is, first we're gonna count the longest carbon chain, and we're gonna start from the right going to the left, since on the right we have a carboxylic acid group. So that would be our first carbon. Then we have an amino on the second carbon. On the third carbon, we have an alcohol group or hydroxy. And then on the fourth carbon, so our longest carbon chain will be a butane. So naming it, we'll start with the amino. It'll be 2 amino, 3 hydroxy. And then the carboxylic acid on the right, since the longest chain is a butane, it'll be called butyric acid. So the full name would be 2S3R, 2 amino, 3 hydroxy butyrated acid. And then some of the physical features on it are the weight of it, as like the molecule would be 119.12 grams over moles. It's soluble in water, and whenever you see it like in the physical form, it's like a white powder or crystal. So here we're going to talk about the molecular and structural formula of it. So the molecular formula is C4H9NO3. And then for our carbons, we have, going left to right, we have a primary carbon on the left, then a secondary carbon, then another secondary, and then a primary. And then the hybridization of each carbon or molecule part of it would be on the left is going to be an sp3 carbon, and then another sp3 carbon, sp3 oxygen, and then another sp3 carbon, sp3 nitrogen. And then on the right side, where another primary carbon would be, we have an sp2 hydrogen on the top. That primary carbon would be a sp2, and then on the right we have an sp3 carbon. And then for this molecule, we have 3 functional groups present. We have, on the left, we have an alcohol and OH. And then we have an NH2 being a secondary amine, since the carbon is connected to is a secondary carbon. And then on the right hand side, we have a carboxylic acid. So our electronic properties, we're going to start with our amino, the NH2. It has the lone pair present on the nitrogen, allowing it to attack with bullets, which can cause a reaction with our electrophile. So our nitrogen is going to act, or our amino acid is going to act as our nucleophile. From there, it's going to attack the peptide bonds with the carboxylic carbon, which can form a substitution. From there, that carbon is going to be vulnerable from the attack from the nucleophile, the amino acid, and since that, the carboxylic acid is going to act as an electrophile. The OH from there, from the carboxylic acid, can be given, which is going to make the OH into an O positive, which from there is going to cause ionization to turn the COH into COO minus. While the hydroxy is going to act as an H plus donor or acceptor, which is going to help with the stability of the molecule. And since it's an alcohol, it's going to help with the solubility. And here we have the chirality of the molecule. Here we're going to have 2 chiral centers, one on the amino acid and the one on our alcohol. Well, we can start from the alcohol. Our alcohol is going to be our first priority, since it has an oxygen, is the biggest one. So from there, we're going to go, that'll be number 1, and our hydrogen is going to be our number 4. After that, we're going to look at our carbons. The left carbon has a CHHH, so it has 1 carbon, 3 hydrogens. And the carbon on the right has a CCHH, so the carbon on the right will get the second priority. So if we're looking at it, we're going to go 1, 2, 3 going clockwise, so it would make it an R. And then if we look at the next, what I call it, chiral center, which is on the nitrogen or on our amino, we're going to count the nitrogen as our first priority and then our hydrogen as our fourth. And then after that, we're going to look at both our carbons and see which one does have more priority. Since they're both carbon, we're going to go on to the next thing. So the carbon on the right has a COO, and the one on the left has a CO. The one on the left has a CCO bond, and then so the priority to go to the carboxylic acid on the right. So we're gonna count it 1, 2, 3, going counterclockwise, which is gonna make it an S. So here we're gonna have an R and an S. So that would be our chirality. And then from there we're gonna look at the enantiomers of it. So this is the original molecule on the left, which is SR. And then this is the enantiomer on the right, which is going to be RS. Since they have different, chiralities, or like different R and S's, they're both completely different molecules. So the one on the left would be L-threonine, and the one on the right would be D. They both do different functions since they're both enantiomers. So its role in our biological system for commercial use, it's used as a peptide synthesis. Threonine is used to create peptide bonds for the use in pharmaceutical research, and it works by taking the amino NH2, which is combined with the carboxylic group. Since that carbon is connected to a peptide bond, that's where it gets the peptide synthesis. And then in our body, it can produce hydroprolane, which that hydroprolane helps helps stabilize collagen. And it works by giving the proline an oxygen atom from the threonine, which in turn becomes hydroprolane, which is used in collagen and promotes tissue healing. And that promotion of tissue healing can help close any wounds that we have in our body, like let's say cuts on our fingers or just cuts in general. It'll help it heal faster. Threonine is also involved in numerous metabolic processes. As a result of it, it interacts with other amino acids such as serine and glycine. So here we have the structure and function relationships. We're going to start with the NH2. Since it's the amino and nucleophile, it creates bonds, helping in protein synthesis, while the OH helps stabilize the protein so it all runs smooth. The OH also helps with most functions like protein stability, tissue repair, and enzyme function. The tissue repair, going back to the collagen again, it helps it from there. It's like if you have a cut, it'll help heal it and so on. The OH also bonds help form collagen and glycoproteins to keep the structures and maintain function in the tissue repair. So the future of the amino acid threonine, it helps in maintaining metabolic balance, collagen synthesis, which promotes tissue and wound healing, is one of its primary functions. It also stabilizes collagen and promotes tissue repair when it forms with proline. With this, a medicine for skin to regenerate or repair may be possible in the future. I think since it helps a lot with collagen, which in turn helps a lot with tissue repair, so I think it might be possible later down. It also is essential in farm animals since it helps with protein synthesis and so on. They put it in their food because these animals need protein so they can grow bigger, and it also keeps them healthy for the future. So to end my presentation, in 1926, biochemist Samuel B. Shriver and botanist H.W. Buston of Imperial College of London, they found the amino acid threonine in an oat. And threonine helps in the production of proteins and the operation of several enzymes in the body. The synthesis of collagen is where I think threonine is used the most, or is like there's the best use of it, since ROH or hydroxy in the molecule, whenever it's combined with the proline, it stabilizes collagen and aids in body tissue or wound repair. For that reason, I see threonine important both today and in the future for that reason.